Now in this video, let's try to be more familiar with these notions of sequences. So simply what we mean by a sequence is a list of numbers, and we denote it by an. And a better way of representing these sequences is writing it like this inside the curly bracket, and we write the starting number and the end number like this. So for example, if we have our equation as n divided by n plus 1, then you can see clearly you can see the starting point, which is n is equal to 1. So we start with this number and we proceed according to the given equation, right? So this is the term or the output related to n equals 1, and this is the output related to n equals 2. Or in other words, you can say this is the first position, this is the second position, this is the third and fourth, and likewise. And the thing is, now you can even start these sequences from a number different to 1, right? Say for example, if we start with 2, the first number that you will get is the output when you substitute n equals 2, right? So in that case, our first position will be this one, right? So in other words, this sequence will be shifted towards left, right? So it's an important thing to understand that for a sequence, it is not a must to start from 1 all the time, okay? And here are some more examples of these of different types of sequences. Now the first one is the one that we discussed before, and there's another thing that I want to mention, which is kind of a useful tool that we use when we represent sequences. That is this negative 1 to the power n term. Say if we need to have a sequence, or if we need to construct a sequence so that the plus and minus signs interchange, simply if we need to write down a general notation for this sequence, how do we do that? So now here the first position is negative 1, the second position is positive 1, and likewise the plus and minus signs interchange. So a way that we can do is, if we start our sequence from n equals 1 and if it goes up to infinity, that means this position is the output for n equals 1, and this should be the output for n equals 2, and likewise. So when it is 1, you need to get negative. When it is 2, you need to get positive 1, right? So in other words, if we directly write down our equation as this one, see what will happen when n equals 1. That means we have a1, which is equal to negative 1 to the power 1, and that is equal to negative 1. And when n equals 2, that is a2, and that is equal to negative 1 to the power 2, you have positive 1, right? So likewise, for all the odd powers, you will get negative 1, and for the even powers, you will get positive 1. But let's say if we start our equation with n equals, if we start our sequence with n equals 0, say for instance, if we start it with 0, you can start the equation from any number, right? That's totally fine as long as it is a whole number, right? So if we start with 0 and if it goes to infinity, and if we write the equation like this, right, see what will happen. Now we have to start from 0. Okay, so but say like our objective should be to obtain the same list of numbers even by starting at 0, right? So if we start at 0 and then the first number will be negative 1 to the power 0, which is equal to positive 1, right? So if we start at 0 and if we write down the same equation, we will not get the same sequence. Then what we will have is the like this is the sequence that we need to have, but we will get everything in the opposite direction. It will start from plus and interchange with minus signs, right? But here we have started from negative and interchanged with the positive and minus signs, right? So what do we have to do if we start with 0? There can be like we can do a very simple change to our equation. See, if we write it as negative 1 to the power n plus 1, then n equals 0 will give you a0, and that is 0 plus 1, and that will be equal to negative 1. And n equals 1 will give you a 0, negative 1, and 1 plus 1, that is equal to negative 1 to the power 2, and that is equal to 1, right? See now, if we start at a different number, we have to change the given equation for the sequence, right? So all these things will matter when we define a sequence precisely. So anyway, like if this is the main sequence that we consider, like this, and this is the first position, right? So the first position can correspond to n equals 0 in the second case, and this corresponds to n equals 1 in the first case, right? So like it's very important to understand these ideas. Okay, now in this case we represented the sequence as this one, starting from 0 goes up to infinity, and in this case we represent it like this, starting from 1 goes up to infinity. So if we start from 1, then this first position and the number or the value of n corresponds to that position will be the same, right? So it's like for the 10th position, that will the required input will be obtained by substituting n equals 10, and that is true only if we start from n equals 1. And if we start from a different number, these two values, the position value and the value of n, which is used to obtain the output at that position, will be different, right? See here, now this is the second position, but the output at this second position is the one that we obtained from n equals 1. Okay, but this is the second position. See, these two numbers are different, but if we start from 1, the first position goes with n equals 1, the second position goes with n equals 2. See, these two numbers will be the same. But anyway, no matter what representation that we use, we should be able to identify or to visualize the sequence properly. Now see, in here you have started the sequence at n equals 0. and this is the way that they have defined the sequence. So we have terms defined accordingly, right? So that's the basic idea you have to get when it comes to the representation of sequence. And there is one more thing that I need to explain, that is the recurrence relationship, which means the term in the front depends on the value of the term in the back. Like now, see, in the previous examples, all these values at each of these positions are independent of the value at the previous positions, right? So, but what if we define relationships like this? A1, now we have the sequence defined like this, right? So we have started the sequence from n equals 1, and we have separately assigned values for a1 and a2, right? So there are no any general n terms when defining the values for a1 and a2. But after that, so starting from n equals 3 upwards, we have defined the relationship like this. So if we write down the sequence in a form of a list, what will happen? Now we start the list from 1, and this is the a1 term, right? And then we should have the a2 term, that is again 1. And how about a3? Now to compute a3, we will need to substitute n equals 3 in the third equation. So it becomes a3 is equal to a2 plus a1, right? That's the way they have defined the relationship. Now according to that, it becomes 2. And how about a4? a4 will be equal to a3 plus a2, right? And that will be equal to 3. So likewise, after the second position, all the other terms will depend on the previous term. Like actually here, all these terms will depend on both the immediate term situated before this one. It's like to compute a10, we will need a9 as well as a8, right? So to compute a certain term, we will need the n minus 1th term as well as n minus 2 term, right? The closest, we needed the closest 2 terms, right? So these type of relationships are called recursive relationships. That means in order to compute a certain thing, we will need the values of the terms before that. Like we might not need 2 values. Like say if we have defined the relationship like this, an minus 1 divided by 2, right? And if we have defined a1 as 1, then our sequence will be equal to the first term. Now when you say our sequence, that is that can also be represented by this one, right? a3, a4, a5, likewise. Okay, so and according to the way that we have defined, a1 will be equal to 1, right? And a2 will be equal to a1 divided by 2. See, to calculate a2, we needed the value for a1, and in this case it is 1, so that divided by 2. And to compute a3, we need the value of a2, right? a2 divided by 2, that's how we have defined. So that will be 1 over 2 divided by 2. right? So likewise, the main point here is to compute a certain thing, we need the values behind, right? So those are called recursive relationships, and in recursive relationship we must indicate the starting point separately, because if we only have this one, we will not have enough data to calculate the starting position, right? Because we don't know the value of a zeros in here, and in fact a0 is even not defined in this case, as we are starting at n equals 1, right? Now here in this second example, we only need we only need one number before this one, but in the example I mentioned before, we needed two values to compute this one, right? To compute n, we need n minus 1 as well as n minus 2, and this sequence, the reason for mentioning this sequence is like if we write down a couple of numbers, it will be like this, okay? And now for this specific sequence defined in this way, this one has a unique name called Fibonacci sequence, right? Now there are several applications of the Fibonacci sequence also, but we are not going to discuss it in here, but it's quite an interesting sequence that exhibits some nice properties, okay, right? And in the next couple of videos we will go over some definitions and theorems related to sequences.